So, as he said, I'm Gary Sieling. I work for Element 84. We are a software consultancy based in Alexandria, Virginia. We do a lot of custom software development work on AWS. And many of our clients are government agencies, notably including NASA. And internal to the company, we have a lot of experience working on geospatial systems, and some of those experiences have informed the material for this talk. And there's two open source projects I want to call out notably because I used them for research while I was looking at this talk, and they're things that we've worked with. So Cumulus is a tool for moving, for ingesting collections of satellite imagery into the cloud, like from other data centers. And Pingeo is a community platform for big data geoscience. And so that's something that you could run locally. That's Python-based. But it's something where you would use the cloud to scale data processing work. And before I talk about the experiences we have, I want to reflect a little bit on some of my experiences as a software developer over time. So when I was in college, probably like a lot of people, I had a MySpace account. And for people who remember this or don't remember this, the original site was pretty unstable. So you'd click through these screens, you'd periodically, it would feel like the site would crash a lot. But the other thing that was interesting about this was that you could extensively customize the themes on the site with JavaScript and HTML and stuff. And so what would happen is that people could construct fairly simply phishing attempts. So you would click through the site and you'd randomly land on some page that looked like a login screen, and someone would try to trick you into giving out your password, which is, of course, unacceptable in a web development environment. And our expectations, I think, since then of the software that we use has changed pretty dramatically. And one of the things that I remember is a notable conversation I had with a tech executive is he said, I've got developers on my teams building things for me, and I say to them, why can't they build things that are as good as the iPhone? There's, of course, some challenges to that, but the things that we have been exposed to as consumers have changed our expectations of what we expect when we're the consumers of software, and so those of us who are building software for other people get those expectations pushed down onto us. But there's still a lot of work to be done. This is a graphic I found online of some famous data breaches, and I think the Yahoo one's pretty famous because it affected basically everybody. Of different, and probably at this point, most of us have had some piece of personal information about us in one of probably multiples of these data breaches. And so because these are becoming really famous, this is also like the MySpace example. Of course, you see that they're one of them. But this is something which creates some back pressure on those of us who are developers, even if we're web developers, to think about security in some way in our applications. But one of the challenges from a business perspective is just the cost of dealing with these things. So I pulled this quote from the Stack Overflow yearly developer survey, and it says, DevOps specialists and site reliability engineers are among the highest paid, most experienced developers, most satisfied with their jobs, and are looking for jobs at the lowest level. So the challenge here is if you said, I'm doing web development for clients, and we want to have some people who are like experts in security or in the stability of the system that we're building, there's people you can hire, but it's challenging, and we need to be able to build things which are viable products for our customers. So I'm going to talk about building serverless software. So this serverless here, meaning in the general sense of there's no servers, not necessarily the framework specifically, although it can be. And so there's three objectives that I want to talk about in building something which is robust for our clients. One is that it's stable. That means that users who are using the application don't feel like there's a lot of bugs. The second is security, which is something that probably everyone's conscious of, but it's sort of off to the side where you might have some experts who have to pay attention to it, but it's something that has to still be thought of through the entire software lifecycle. And the third is the affordability aspect of it, which isn't necessarily something we think of a lot of times when we're planning out software projects, but maybe should, because in order for all of us to have jobs as software developers, the business that we're supporting has to at least be viable. And so I'm going to talk about some work that we've done processing satellite imagery as a case study. So this is an artist's rendition of one of the Landsat satellites. These are a set of satellites which are owned by NASA. They're supposed to be about the size of the bus. They have a bunch of sensors on board which collect imagery in both the visible and non-visible spectrum, which is useful for a lot of scientific purposes. And this generates a lot of data. To kind of get a sense of the scale of this, there's an organization called Digital Globe which has a bunch of their own satellites. They did a talk at an AWS conference where they talked about the scale issues that they run into. And one of the things that they said is that they were generating about 80 terabytes of data off these sensors on the satellites a day, and they had about 100 petabytes stored. So there's a lot of data to work through. And what's coming down from these vehicles is essentially just some sort of raw data from whatever the sensor is in the cloud. But the processing pipeline that happens here is fairly simple. And it's going to be, I think, as I go through, it'll become more apparent how this is sort of relevant to JavaScript development, because you have that initial phase where you've got some raw data, you convert it into something that's more recognizable to us, like TIFF files or JPEGs or something, and then those are converted into something which is called a product, which is a form which is more usable, say, for a scientific purpose or just for generating maps. And the final result of this is that we have a collection of images which are called tiles that are at a size that we can use them for web development. And we also probably have some metadata around them. So the tiles will have like an X and a Y coordinate, a zoom location. If it's a series of time images collected over time, they'll have some timestamps with them. Maybe if it's a collection of imagery from different satellites or different drones or something, then you might also have some information about the vehicle that collected them. And so ultimately, we want to build applications which look like Google Maps. From a web development standpoint, if we think about how we would build something like this, there's a layer that's the imagery. There's a layer over top of that which has vector data. There's some push pins or icons and text and stuff as a layer that notes interesting places, and then there's a layer of UI controls. And internally, we've been using a library called leaflet.js. This is the React version of it. It works pretty nicely. The React version of it is literally what I just said. There's objects for each of the tiles. You render this, and you can produce a map. And one of the things I think is not necessarily apparent when you're talking about mapping applications is that it is actually a reasonable thing to do to have multiple layers of these images. So this is, there's a open source project called Open Drone Map, which you can fly a drone over an area and construct something that's like Google Maps with the images you collect with the drone. And they took some historical imagery that was collected as aerial photography and did this exact thing and then overlaid it on top of a map just for like a historical research project, which I thought was kind of cool. So when we're working with mapping data, AWS is really appealing because for two reasons. One is that you can scale up infinitely. So if you wanted to process imagery of the entire Earth, you could get the resources you need to do that. It's also appealing because you can scale down as far as you need to go, potentially to 0. And the reason that you might want to do that is if you were building applications for people who are responding to natural disasters, there's a lot of interest during the time of that event. If there's a hurricane or a forest fire or something, while that's ongoing, there's going to be a lot of people who are really interested in that data. Then when that event is over, people become not as interested in that. So working within the cloud environment gives you the ability to scale up and down. So through the course of my career, we've seen some changes in how people do development. I started out doing Delphi development on desktop applications, and in that context, when you're writing software, you have to compete with whatever else is on the end user's machine. In the case of mobile development, our constraints are around the size of the device. So we want to be able to scale the design of our application such that it fits in the allotted space. And in something like IoT, the constraints are around the network connectivity. So we know that we might have a device that can only phone home every once in a while. And so all of these different development paradigms impose constraints on us, but the cloud's a little bit different. Intuitively, we kind of know that we're all just renting servers from somebody else, and I stole this off the internet, in case anyone wants to know where I got the drawing. And I found this nice illustration of a sort of path that people take as they start to use something like AWS. So you might start out saying, I'm going to store some files on S3, I want to use some virtual machines, and then you start reading the documentation to figure out how to use it well, and you realize that there's tens of thousands of pages of documentation, and quite a bit to go through. And so we need a way to think about how we're going to do development in this environment. And so I like this, this model I found in an article which explained how networking works in AWS. If you think about a software development stack, when we say we're a full stack developer, a lot of times that means I do front-end work, I do back-end work, I might do some stuff with the database. But underneath the database, there's more layers, there's the hardware, there's virtualization. And then above it, our application, there's also potentially SaaS products we use. So we might all use something like GoToMeeting or something that we rent from someone else. And if you're using a cloud vendor, they have products at all layers of this stack, and you can, potentially at any layer, you can bring your own thing or use what's provided. With a few caveats, you of course can't bring your own hardware and stick it in AWS's data centers, but you can if you have your own, if you were working for an organization that has a data center, you could link yours to theirs and have the network kind of feel like you're on the same network. And then sort of at the higher levels, a lot of us are thinking about like how we're going to do something like serverless, so we're talking about writing functions in Lambda or something. But what's neat about this is if you work for a large organization, a lot of these different layers of the stack are managed by different teams. So you might have a team that's responsible for the data center and a team that's responsible for databases and so on. But if you're using something like a cloud provider, you have all of these things at your fingertips, assuming that you have the access within your account. So that if you might say, I'm a front-end developer, but you know what, I can, because I need this piece of functionality, I can set up a private network link to a customer's data center if I need to. And in a big company, that's very difficult. So if you reflect back to the slide I showed where I had 3 pillars of robustness, I have the first one I'm going to talk now about is stability, and this is kind of an area that's our primary responsibility because we might be paged or at least get complaints from our customers if something doesn't work. So for the applications that we're building, we've converged on a lot of projects on this sort of general architecture where we have some sort of single page application running on static hosting that would be S3, maybe CloudFront in front of it. We've got serverless microservices sitting behind that, and there's different frameworks that I've worked with that do this. And then you might have, a database you're relying on the provider to handle things like high availability and backup. So you're kind of outsourcing some of the DevOps work. And then, like I said, you frequently see things where you've got private links to customers' accounts or data centers or something if you need to do integrations with their products. And one tool I want to call out here is Gatsby. We've used with a good amount of success. It describes itself as a blazing fast modern site generator for React. And so I sort of just think of this as a nicely put together starter kit tool. One of the things that I really like about this, aside from being a nice way to start out a project, is that it wraps Webpack internally, and so if your project goes well, you might never have to actually edit the Webpack files again. And the assumption here, of course, is that you've got REST APIs living kind of side by side with it. So I joined Element 84 relatively recently, and so this concept of microservices is something I've been exploring through that time. And one of the things that I like from a DevOps perspective is that you, without necessarily realizing it or doing very much of it, you have multiple copies of your application or the individual service potentially running at a time. So if one of them crashes, it doesn't affect the other ones. We've sort of converged on a path where each of the services is sort of more or less corresponds to a module. So it's not like every single function that your application does is a different Lambda. It's component-based. And one of the things that's also cool about this microservice concept is that it gives you the ability to switch out some of your APIs for a different API, meaning you could, for instance, pay a vendor to do the same thing that you were doing, or take something that you were paying someone and swap in your own thing. And there's, which swapping out an entire API to me sounds like something that would be unrealistic, but in the course of working on these projects, there is actually a really natural use case for this. So this is an image of one tile that you would have if you were rendering a map. And in this particular case, this is a small subset of a very large image. And the image itself, if you were to pull the image that this tile came from, is 1.5 gigabytes. You wouldn't want to pull that all down in your browser to render a map. You just want to pull down a little piece. So the way that this works in this particular, in the demo that I was looking at, is they're doing byte range requests from your JavaScript code to S3, pulling down just that section of the tile and rendering it. And so an API to get tiles is pretty simple, so it's relatively easy to swap in and out different ones of these. And there are, in fact, some hosted providers that you can use. So you could build an entire application using a trial version of something that's out there, or a paid version of something that's out there. And if your client or your project matures to the point where that's no longer what you want, say you want to provide your own tiles, you've done some machine learning thing on them and marked them up, you could replace the provider with your own tool. And so you could do something like, you might just have a folder structure that sits behind a zoom level on a location, or you can do the byte ranging thing that I talked about. But the point here is that you can swap any one of these three things in for any of the others. And so the last note that I want to make here on the concept of stability is, all right, good, slides up there, is this notion of DevOps. So this is a example taken from a tool that AWS has released relatively recently. They call the Cloud Development Kit. This generates, if people are familiar with AWS, this generates CloudFormation templates. But you can write JavaScript code to say, this is what I want my infrastructure to look like. This generates a script you can then run to build that. And so what I think is cool here is that you could conceivably do your web UI in JavaScript, or this is TypeScript, but you could do your front end in TypeScript, your back end in JavaScript or TypeScript, and you could do the DevOps work that way too. So this is at least a familiar entry point into that world. So the second concept I had as an objective for building a piece of robust software is security. But this is we have to take a different approach to this, because this isn't really germane to most of our responsibilities as web developers. It's like security kind of has to be something that's considered when you're building a product, but it's not necessarily something you would expect everyone to be an expert in. It's just something that has to pervade the software lifecycle in some way. And so here, the approach is very different than something like robustness, where we take, or something like the stability of the software, where we take a lot of ownership of it. Here, you want to limit the ability of an attacker to do damage. And so something like Lambda is appealing that way because you don't have any servers to manage. You've just got this little box that can run code. One of the things that people tend to find frustrating, I think, when, say, people who are pure JavaScript developers join a cloud native project, is that you end up being forced to learn about how security works within AWS. And the reason that you're forced to learn it is because by default, none of your services have access, or your user accounts no one has access to do anything. And so you have to figure out, what does this service need access to do, and how do I do it? But one of the things that's really compelling about that model from the artifacts it produces in our development repositories is that you as a developer will, say, choose to work on a feature, pull a JIRA ticket, maybe make a branch or something for that ticket. In the course of doing that, you might say, here's my feature, and then also here's the additional grants that I need in IAM to allow my feature to work. And what that gives you is, over time, you build up this audit trail that says, in my Git history, this permission was added to support this feature, and so you can find out why exactly a permission exists, which I think is, from looking back retrospectively on projects, is really compelling. And then the third thing here is that ideally, when in the cases where the AWS product you're using is implemented thoroughly, you can outsource a lot of the difficult parts to them by checking a box. So that means things like database backups and other things in that nature. So when we're talking about writing Lambdas, and I'm using the term a little bit ambiguously here because this is just a natural JavaScript Lambda. They're conceptually very simple. So this is a Lambda that has no side effects. It just multiplies two numbers together. Conceptually, something that's maybe more relevant to most of us is we might build a Lambda that returns some JSX code. Or we might, if we were doing back-end development, we might have a Lambda that, say, updates something in a database. And this isn't necessarily valid syntax in any language. It's just a demonstration of what you might expect on the back end of this. If you're coming from this perspective of this is what a Lambda is in JavaScript, then using serverless projects in AWS Lambda will become frustrating because the code that you're writing, while it looks like one of these Lambdas, lives inside of a box that AWS, or if you're using some other provider, provides for you. So as an example, if you do console.log in the browser, we all know where that goes. If you do console.log in an AWS Lambda, then that's going to go off to the logging products that AWS provides, and then you got to go figure out where it went, where your messages went. The code that you're writing lives inside of a container, something like a Docker container, and so because of that, it has natural limitations imposed on it as walls. And so as you're writing code, you might bump up into some of these. You run out of memory, or the thing doesn't run as fast as you would hope. And that's where you start to see the differences between a Lambda in JavaScript and a Lambda in AWS. But all of these are important from the perspective of thinking about security. So for instance, by having limits on the amount of memory and CPU you're providing your application, if you just get just as much as you need, if someone were to find a way to run a Bitcoin miner in your account in this context, they would get very little out of it. Maybe not nothing, but they would get very little. And similarly, they provide limits on what the thing can talk to, so you control the network that the Lambda has access to, and you control what APIs it's allowed to hit through security groups. And then that controls how the thing's allowed to escape out of itself. And of course, if anybody who's used Lambda knows that people talk about the issue with cold starts, that's a natural consequence of this having a network interface that's attached to the container that you're using. That's a sort of a portable network interface. So the third concept I have here in building something that's robust was affordability. And before I talk about the tools that we have at our disposal to work with this, I want to talk about why this might be important. So this is a demonstration tool that a group at Element 84 has been working on called Headlamp. And the idea here is, imagine you had a customer who is a first responder to a natural disaster, in this case a forest fire. You need some sort of dashboard to know like what's happening as you're responding to this event. So like in this case, it's showing you the extent of the fire. And what's a little bit hard to see because they're fairly small is there's some push pins of known locations of some events. So the idea is you have a call center, people call in, they say, hey, my horse is missing or my dog's missing or something, and someone makes a mark on the map so that the person who's trying to allocate resources has a way to respond to this. The tricky thing about working in this environment is that you need to run some code. Your website or something needs potentially to run on something that's run on site at this location because the network may disappear on you. That was great timing. But you also, a lot of these organizations have drones that they use to survey the area. And so this is an example of a path, just from some marketing materials from a drone company, of a path a drone might take to survey a farm field. You're basically going back and forth over it, collecting images as you go, and then stitching those together in software. And the stitching it together part takes some processing time. And so if you're in this natural disaster situation, you need to decide, do you want to try to set stuff up on people's laptops? Do you want to ship all that to the cloud and work with it? And a lot of these projects which involve working with either satellite imagery or drone imagery or something like that have some sort of processing pipeline. So regardless of the actual business needs, you have these basic three components. One is what is termed science code, which is almost always Python code, and that does the math-heavy work. Typically, that code is wrapped in a Docker container so that if you have a DevOps person, you can just take that thing and treat it as a little box that you ship around. And then you have some sort of glue code that governs how this processing pipeline works. And a lot of times what I'm seeing in the open source projects that are out there and the private commercial projects is that there's this is all just JavaScript and things that we're already talking about. And then there's always going to be additional web development work just to monitor how these processing things are taking, how long, what's happening and where the errors occur and that sort of thing. So just as an aside, I have a couple of examples of what the science code looks like, just because this is pretty interesting. So one very basic thing that you need to do is to project the images from around Earth onto something which is flat that we can use in a web UI, which would obviously be the third option here. A second thing which is also pretty valuable is to say, have these things sort of called ground control points. So this is, you have a marker or something on the ground where you know where this is, like the latitude and longitude or something. And you want to find that in the images you've stitched together from these drone videos or something else. So that you can either overlay it on top of images you already have, or so you can just do measurements between different points on the ground. So one way or the other, regardless of what you're actually doing in this processing pipeline, you need the ability to scale the thing up and down. You need the ability for servers that crash to be replaced, or if you're using somebody's laptop, you need to be able to handle them shutting it down, adding new ones to the processing queue, be it as it may. And so the way that you would solve this is with some sort of queuing system. And so here I've got an example of this is what would happen if you're using SQS in Amazon. You have a queue, you pull events off of it. Internally to something like Lambda, this is what's happening for you. You've got your reading events as they happen. It's doing this for you, or you could construct this yourself, depending on how much control you want to have over the infrastructure. But fundamentally, when I'm talking about affordability, regardless of the number of products that your vendor has, you are paying for some combination of these resources, which are CPU, memory, disk, and network. And so the more you use, the more the provider makes, of course. But when we talk about building something that's a robust piece of software for our client, we want to be able to match their workload to the products that the vendor provides to us, so that we're not paying for things that we don't need. So most likely, if you work on a team that does some form of agile like Scrum, you're doing some sort of estimation process, and in that estimation process you say, I'm going to build this ticket, I want to add a screen to the UI, and you estimate the story points, and that's this much time and risk. This is going to take me a week, but I'm not sure, or something like that. But conceivably in the future, because I want to add this screen to the UI, that means I need to add this number of new services that sit behind it. It's going to cost this much for API gateway and Lambda and the storage and logging and whatever sits behind that, so that your business owners can either say, I don't want to build that because it's going to be too expensive, or maybe we should change the design so that we can influence that behavior. So this is an image of a tool which NASA provides to search for satellite imagery. And what you're seeing here, the area in green is areas where they've generated some product. And the product in this case is something which shows you an illustration of how much vegetation there is in different areas. And so as you might imagine, the interest in this is not necessarily, you don't necessarily want this product generated for the entire Earth. So they give you this interface where you can search for what is available to you. and filter based on the time range. And what's interesting about the imagery that comes from like the government space programs is that these go back potentially decades. And as a sort of reflection for me, I think this is interesting because a lot of the things that we build as software developers aren't, maybe a decade is how long they'll last for. I think I may have worked on one product that was intended to last that long, but a lot of times I'm not sure that we necessarily think about that as the longevity of something as being important, because it's usually something that's decided outside of us as a business decision. So I want to leave as a sort of reflection, if we were to think about that example I have of a piece of software that's used for mapping for disaster response scenarios, if we're going to do something which is hopefully making the world better after we've left it than when we started, how can we ensure that those things last as long as is possible? And so like in the JavaScript ecosystem, kind of one of the challenges here that we have is there's a lot of churn. So there's lots of new libraries. There's always new libraries. I don't think I've ever worked on a project where for 3 to 6 months, at some point during that project, something underneath us, one of our NPM dependencies broke, and you end up on GitHub trying to talk to the developer, trying to figure out what's happening. I don't necessarily know how to fix that problem. I wish I did. But I think as a thought experiment, it's interesting to say, we know that things are changing around our software. If I was to walk away from the project I'm working on and no one touched it for 6 months or a year, if I came back, would it continue to build? Would our build tools continue to work? Would npm install still work 6 months or a year from now? Obviously, we can't know that answer to that question, but our ability to keep that working is important from the business perspective. And similarly, if I can deploy my software today, will I still be able to 6 months or a year from now? And the third question about it continuing to work is more about, will the browser world around us change so much that our applications don't work anymore? I don't have answers to these things, but I think there are some reflection questions I wanted to pose. So that's my talk.